And we're back. Happy Thursday. Today, we are going to switch gears and we're going to talk about ensemble methods. And ensemble methods are a type of classifier induction classifier creation mechanism in our pipeline for pattern recognition system. And it's a kind of meta learning techniques where it's going to aggregate a bunch of individual classifiers. So why don't we begin? Administrative. This is based on some work I did with my advisor, which was the subject of my PhD work. And so I direct you to this paper, Training Ensembles Using Max Entropy Error Diversity, in Proceedings of the 29th International Workshop on Bayesian Inference and Max Entropy Methods. I have that link available on the course Blackboard site. All right. When the decision is very important, human societies often rely upon the opinion of groups, whether it's things like voting, choosing leaders of the country, or it's ascertaining someone's innocence or guilt, potentially taking away his or her rights. We always rely on the opinion of groups. So why is that? Well, it's because an individual makes mistakes. And because an individual is prone to erroneous judgments, you don't want to leave it up to just one person. You want to have a group of people, committee of sorts, render that decision. And so what are some of the properties of these group decisions? Well, first of all, you get redundancy. All of the actors in the system, they compensate for the error-prone individuals among them. And whenever you have a group of people that arrive upon a mutually agreeable solution, it tends to be very broadly or more broadly applicable across a wider range of scenarios. So let's take a look at supervised learning and ensembles. So this work stemmed from a collaboration I was doing with Bigelow Lab for Ocean Science, Marine Science Research Lab in West Boothbay Harbor, Maine, the Computer Vision Lab. I was in the Machine Learning Lab, and it was to take water siphoned directly from the ocean, put that through some sensors that would detect microaquatic organisms, and then the idea was to classify them, to sort of take an ocean census, as it were. Now, of course, phytoplankton and zooplankton, these microaquatic organisms, they're the foundation of the marine food chain, and they're also important for trapping carbon, essentially acting like a blanket for the Earth, regulating the temperature of the Earth's waterways. And so you have in these images are actual images from an apparatus made by our collaborators, of Bigelow Lab, called the FlowCam, and these are actual pictures of phytoplankton and zooplankton. And so we extract attributes, all sorts of visual attributes from these images for height, width, texture, shape, so forth. And the idea is then to build a system that will classify them, essentially to choose our features such that we can discriminate well between organisms of different species. And so before this, how this was done is that you'd send out graduate students and you would get water samples from different depths in the water column in various locations. And then you'd prepare slides and sit in a lab with a clicker and interpolate based on the count for you human recognizers, as it were, of these microaquatic organisms. And so we use supervised learning, and as such, supervised learning, we have our data set, and these instances are drawn using features, real valued in D dimensions, and we have some number of samples, big N, come in from the FlowCam, and we have a set of ground truth labels, the labels drawn from a finite label set from K classes, and these classes, K, are all the different species under study for the microaquatic organisms. And so we take these labeled instance pairs in our training set, our in-sample points, and we input them through what I'll call a classifier inducer. That's that box that we talked about that searches for your final best hypothesis. And because it is an estimate of the ground truth class label, we're going to call it F hat. Hat means estimate. It inputs your feature vector is x, and it's parameterized by some parameter vector theta resulting from the learning algorithm search, and it gives you a class label estimate y hat. And so we're given a set of labeled instances, and we want to estimate or learn a function that maps instances to class labels. And the idea is to do so by minimizing the training error by action of your learning algorithm. So graphically, we want to set out to arrange data in categories, birds of a feather flock together, so to speak, so that data points within a class are more similar to one another. We're going to use that fact and also data points that are in different categories are further away from one another in feature space or less similar. But the problem lies in these instances where they overlap. These are the so-called confused instances where a lot of methods have trouble. And so one of the ways we can address this is with so-called ensembles. And an ensemble is a set of classifiers. We input the data set, so we have classifier inducer 1 through m. So we have m of these classifiers we're going to build from the data set. We're going to estimate final best hypothesis f1 hat through fm hat, parameterized by feature vectors theta 1 through theta m. And then these individual component classifiers, we'll call them, we combine their estimates through a voting mechanism. And if we can come up with a suitable voting mechanism to combine these estimates, we can get an aggregate estimate y hat resulting from that vote that improves the accuracy beyond the individual accuracy associated with a single component classifier. And so these classifier inducers, an important fact to remember, is that they try to minimize training error, or in-sample error, as it were. And so the goal is to try to aggregate a bunch of component classifiers such that this resulting aggregate label is associated with a lower error out of sample than any of the best of the individual component classifiers. So that's what we're after with an ensemble. And this idea of combining estimate, it lends itself way back to the late 1700s with the Condorcet Jury Theorem. And it's based on the premise that jurors are neutral. They're not influenced by one another or by the same factors. A juror that is competent is one that makes the quote-unquote correct choice relative to ground truth most of the time. So what does this mean? Well, we know ground truth, if you're in a jury, the person who's on trial is either innocent or guilty. And let's call the competence the probability, PI, to the ith juror that the ith juror is not correct. And so to be competent, a juror has to be correct more than he or she is incorrect. So that means the probability that they are correct is greater than 50%. Okay, so given this set of jurors, each one can be either correct or incorrect, 1 or 0, like flipping a coin. And so we aggregate the error for the jury as being the area under the curve for the error for the ensemble as being the error under the curve for the binomial distribution, because the juror being correct or correct is depicted or modeled as a string of ones and zeros. Each one of the jurors' correct or incorrect outcome you can think of as the flip of a coin. And so here we have the error for the ensemble is the area under the binomial curve for the simple majority and ceiling n over 2 through the overwhelming majority, all n. And that's going to be the error for the ensemble. And we're looking at the error rate for the ensemble based on the error rate for the individual juror. So when we calculate this error for the ensemble, if we have an ensemble of 3, and let's say we have an error rate for a juror of 20%, well, with the 3 ensemble, we get the error for the ensemble, this expression, is roughly 10%. So we have a roughly 50% reduction in error just by relying on a group of 3 going with the majority on through the overwhelming majority. So we know for an ensemble of 3, we get a 50% reduction in error for the group. And if the competence of the juror, if they are competent, meaning their error is less than 50%, in the limit, as you increase the size n of the ensemble, the error for the ensemble goes to 0. If the jurors are incompetent, meaning they are wrong, the error is greater than 50%, they're wrong more than they are right. In the limit, the error of the ensemble, as n goes to infinity, the size of ensemble, or the size of the jury, the ensemble error is equal to 1. And if the juror is completely on the fence, they're wrong and they're right at the same rate, in the limit, the ensemble does not afford you any improvement in the outcome. So this idea of combining estimates can reduce the error rate just by the nature of this idea of competence for a juror. Okay, now certainly when we plot this out, we look at the size of the jury and we calculate on the vertical axis the total probability associated with the non-majority error. So that means you can tolerate a certain number of errors in a jury, that's the non-majority, and they will still be correct. And one thing interesting happens. Well, in the US, a jury consists of 12 people, and when we project up from 12, we see that the error for the non-majority is roughly just about 95%, which means statistically assured. And with this non-majority error associated with a jury of size 12, that means 1 minus that is the error of the majority. And so what this curve says is that with a U.S. jury trial, you do pretty well in terms of the majority being correct or the non-majority error. It's very unlikely to have the majority in error given a jury of size 12. And you notice as it increases, it approaches an asymptote of being the non-majority is 100% correct, 100% incorrect, meaning that majority is never incorrect or very rarely incorrect. And so we ran that simulation, and it does confirm the Condorcet Jury Theorem, and we have an interesting observation about the size of the U.S. jury being 12. All right. Now, certainly, if a jury is incorrect, it means that they have to share some common biases. And in fact, when the prosecution and defense select the jury, they're trying to exploit these biases in favor of their client. And these things might be based on certain factors of the juror pool, things like socioeconomic background, maybe culture, country of origin, and so forth. Because if you can get these shared biases, then they're not going to be independent of one another. And you're going to now exploit the shared biases in order to skew this Condorcet Jury Theorem. So it's based on the jurors being independent, and it's also based on them being competent. And if you can exploit these biases in your favor, you can either show more easily someone is guilty, or you can show more easily somebody is innocent or not guilty. All right. Now, certainly classifiers don't have socioeconomic status and these factors, but still, when we're dealing with an ensemble of classifiers, we want to build the classifier jury, as it were, in such a way that we can break the shared biases. So let's look at how we might do this. So popular approaches for doing this vary the factors that make up the composition of an ensemble classifier. And you can alter all sorts of factors. One is the instance selection, the feature set selection, the classifier induction algorithm, the learning algorithm you use in order to train the classifier, the parameter vector type, or maybe even the class label. There are methods for manipulating the class label. But we're going to focus on methods that try to break shared biases of classifiers in an ensemble, the component classifiers, by modifying the instance selection. And so the two major approaches for doing this are by sampling and by design, a sort of biased or directed sampling. And so by sampling, the technique we're going to use is bagging or go over. And by design, the technique we'll give is boosting. And boosting works by changing the instance selection and therefore changing the distribution over those instances when you pick them for the ensembles in the classifier. And bagging does it by sampling the instances. Okay, so let's look at bagging. Bagging was introduced by Leo Breiman in '96, and it's based on the idea that the underlying classifiers have instability. What that means is that a small change in the training set gives rise to a significant change in the error associated with those classifiers. And so what we do in bagging, uniform at random, we sample from our input training set, we uniform sample with replacement. And this produces what's called a replicate. Now, of course, when you sample with replacement from one round to the next of sampling, you're going to get different subsets of the original training set. And so these replicates then, each one is fed in to the classifier induction algorithm for classifier 1 through classifier M, producing different estimates, F1 hat through FM hat, and their individual outputs of these component classifiers are aggregated with a uniform vote. So 1 vote per component classifier. Now, as such, because they have different replicates, different subsets of the original training set, they're going to commit different types of errors, these particular component classifiers. And then we take the aggregate, which is the result of that vote, the majority opinion, as the output of the ensemble. And so we trained each classifier, each component classifier in the ensemble with one of these replicates. Boosting is a little different, and boosting was introduced by Freud and Shapiro in 1996, and you start out with a set of weights you associate with each one of the input data points. And so here we have x1 through xn and many data sets in your in-sample data. You notice the weights are the same, and you compute a distribution for that. So it's initially uniform. So now you take that distribution and you use it to sample uniform at random with replacement from your data set. Now, of course, it's uniform because it starts out as uniform, but these distribution weights will be changed over time. So you produce a sample from that first round to produce a replicate of sorts, input it to a classifier inducer, you produce your first classifier, final best hypothesis F1 hat. So then when you are training that first classifier, that classifier made some mistakes on those in-sample points. And so those places where you made mistakes, you increase the weights or boost the weights. This puts more probability mass on those instances where the errors were made, the more difficult instances. And when you do so, this redefines the distribution. So you recalculate the distribution, and on the second round, you sample from that second distribution with increased focus on selection of those data points that are more quote-unquote difficult. And those difficult instances tend to be those that are at the boundaries between the two categories of data. And so you sample from that second version to produce a second replicate biased towards the more difficult instances after boosting the weights associated with instances, input that into a classifier inducer, CI2, to produce your final best hypothesis, your estimate F2 hat. So now you output your new classifier and you repeat this sequence, so-called boosting sequence, again and again and again. You take the errors from that second component classifier, you boost the weights associated with the error-prone instances, and then you use that to create a new distribution to sample, rinse, and repeat. And so you do that some number m many times, so you have a boosting sequence of m component classifiers. And you keep repeating this and build a set of m classifiers. Now, this is based on the weak equivalence theorem by Shapiro, 1990, and it's based on the fact that if these component classifiers are competent, meaning that they are correct more than they are incorrect, if you do this boosting sequence big enough, the error will be close to zero or go to zero. Okay, so now that you have these classifiers you've trained in some boosting sequence, you're going to now aggregate the votes associated with the correctness of these classifiers on their training data, these biased replicates. So you're going to combine the individual component classifier outputs using this log odds ratio. Now, since it's negated, that's the same as saying the log of 1 minus the error rate of each of the classifiers divided by the error rate. So you can think of it as a kind of log odds ratio based on the correctness. It's the number of incorrect over the rate of incorrect over the correctness. And you think about it, those classifiers that were more correct get a bigger vote than those classifiers that were more incorrect. Okay. And it just also follows that the later you are as a classifier in the boosting sequence, the more difficult instances you had in your replicate sample, because the biases are such that you increase the boosting weights associated with the classifiers that more classifiers in the sequence got wrong, i.e. the difficult instances. And so that's how boosting makes these classifiers different, shared biases, breaks them by focusing increasingly the classifiers on the difficult instances. Therefore, their error distributions are different. And so this weighted combination is based on the error rate. And there are many other approaches for manipulating features and instances. We won't go through all of them, but this is a good smattering of various techniques that do this. So let's take a look at the case for a collective approach. Popular methods, namely bagging and boosting, train the component classifiers individually. The classifier inducers minimize in-sample error associated with the individual classifier. But one of the things we found with AdaBoost that you propagate information on where errors were made between component classifiers from one to its successor in the boosting sequence. So that's a good thing. You can kind of use this boosting sequence of component classifiers to coordinate their errors. If you commit an error one place, I'm going to focus more increasingly on my errors there. But one of the interesting things about boosting is that once you propagate this information from predecessor classifier to successor in the boosting sequence, you can't go back and revisit early decisions. But it's still interesting that boosting does so well, which it does, because it shares this information on training step. So if you can collectively train your ensembles, you can kind of repair this issue with boosting in that you can revisit earlier decisions by coordinating where the classifiers will commit their errors. And so the individuals, when you make these collective trade-offs, they might not be as accurate in minimizing individual training error, but in concert, the idea is to get them to compensate for one another. And you can only do that if you collectively train them, because only then can you share information. All right, so look through the literature, and there's a piece of work called negative correlation learning for ensemble classification. And so in a paper, someone was doing regression ensembles, and in this regression ensemble, they were looking at multi-layer perceptron component classifiers, and they were aggregating their outputs to select hypotheses between two different alternatives in a regression model. And so in this, they took the outputs of these multi-layer perceptrons, and we have their outputs for the left-hand output aggregated through an equal vote, 1/3, 1/3, 1/3, and then aggregate for the right-hand output, 1/3, 1/3, 1/3. So they're voting based on the regression networks. And so they instrumented the outputs at these output layers for the individual multi-layer perceptrons, and then measured the covariance between these outputs as we train the multi-layer perceptron over a number of epochs. And so this is the result. I replicated that result on a number of UCI standard data sets. And this particular plot is for the Wisconsin breast cancer data set. And so for the Wisconsin breast cancer data set, built that network, and I measured the covariance matrices for the outputs for the Wisconsin breast cancer. On the horizontal axis, we have the epoch for training, and on the vertical axis, we have the average variance. And what we find is that the average variance drops precipitously as we increase our epoch in time. So if we look to the covariance matrix, well, the average variance along the main diagonal, and we see that as you increase the training, well, our variance on average gets smaller and smaller and smaller over time. That's the average. But we'll notice here the off-diagonal terms get more and more negative. And so here it's being more and more negative, more and more negative. And so this measurement says and confirms actually the publication about regression ensembles is that over time, this uniform vote of these component regression models in an ensemble, they tend to have negative covariance, and correlation is nothing more than covariance divided by standard deviation, and therefore we have negative correlation happening. Now, what negative correlation means is that they're effectively spreading their outputs further and further and further apart from one another in opposite directions. One wants to get more negative, while the other one wants to get more positive. And so this idea of using collective information, because if you think about what happens in this backprop network, well, as you're doing backpropagation, all of the adjustments between all of the edges across this whole network, they're happening collectively. And as such, now you can make that global choice sometimes by sacrificing the local choice for the individual networks. And so this idea of coordination is something that carried forward in my work to try to build good ensembles. Because what we found is that current ensemble methods, back-end boosting, on this problem of recognizing microaquatic organisms from images, it was not working very well. And so my thesis, my PhD work, was a solution for how to fix that. And so this negative correlation we will continue next time and pick back up in our meeting on Tuesday. So stay tuned. With that, as usual, please stay healthy, please stay safe, and I'll see you all on Tuesday.